And for our next speakers, who's also the last speakers for this morning's sessions, Associate Professor Dr. Pruksakorn. It's my great pleasure to introduce you to Associate Professor Pruksakorn, who is from the Department of Orthopedic Surgeries at the Faculty of Medicine, Chiang Mai University. His research focused on cancer, specifically in the area of sarcoma and cancer predisposition syndrome. He also delved into the cancer genomics and proteomics and is dedicated to the discoveries of cancer interventions. In addition to his impressive research work, Associate Professor Pruksakorn also leads as a director of the Musculoskeletal Science and Translational Research Centers, as well as the directors of the Center of Multidisciplinary Technologies for Advanced Medicine, also known as CMU team. With his leadership, the CMU team is dedicated to drive the advancement in medical technologies by development of human resource, as well as establishing various units to support the service and trainings and to serve as the Center of Multidisciplinary Research. Please join me in welcoming Associate Professor Pruksakorn.
Thank you for nice introductions, Professor Nicholson, Professor Holmes. Nice to listen to your talk. It's very good and get a new experience. Okay, and thank you for the organizing committee to invite me to here. Today, I would like to share some of my research because of my background is orthopedic surgeons. And I focusing on the one of the deadly cancer, that's the osteosarcoma. So the target discovery after I know the genomics or proteomic technology is make me enthusiastic to study, because this tool is very powerful for me to get the new target. The target for me is doesn't mean just only the drug target, it's also mean the biomarker as well. So a little introduction for the osteosarcoma. This is the most common bone cancer is occur in the children and young adults. And when it occurred, because of the mutations of the osteoblasts, and it's keep growing and damage the bone. And this is the histology of this. This is the typical sarcoma, the cancer cell that produce the bone matrix, but the bone is never well organized. It comes with a huge mass. So nowadays, the treatment of the osteosarcoma is starting with the neoadjuvant chemotherapy, and then we do the surgery. For sure, the eye knife from Professor Nicholson will help me get a good margin in the future for sure. And after we do the surgery, after the surgery done, okay, the patients around 65% will get killed, but the other would be fail. The most common mode of failure is lung metastasis of this picture. So let's go back to a century before. Osteosarcoma is just know that this is a bone cancer, and on that time the treatment is an amputation. But the amputation is just only able to kill the patient just only 20%. This is published in New England Journal in last 50 years. The first chemotherapy introduced, and they can uprising the survival to another 20% to around 40%. And then they push us get into the chemotherapy era. And this is the current situation. The survival rate of the osteosarcoma is uprising to around 60%. From the longitudinal analysis of the survival rate across the decade, we found that this is at first introduction of this disease after the chemotherapeutic era. And this situation is mean that the chemo help a lot to improve the survival. And then whatever, no matter you change the medication, you change the chemo, do adding new chemotherapy, the survival rate is still be the same. So on this side, we need a special approach. And that's why this come with my interesting research project to new discover the way to getting the survival rates get higher. All right. When I first come back, we still don't have any much about the data of the osteosarcoma in Thailand because we know the cancer. Khon University is a good, very good prototype because if we can know understanding the pathophysiology, the prevention is much better than the treatment. Okay, we have to go in that point first because if we know that what is the cause of the osteosarcoma and we can do something about the policy, it will help improve a lot. We try to study the epidemiological data of the osteosarcoma across Thailand, and the result is the same. The osteosarcoma is a cancer of the mankind, or whatever race, geographic area, or food, or any products. They cannot the same of the prevalence of the osteo equally across the world. And the characteristic of the disease also go with the same of the world data. Okay, but the one things that the study can tell us, that is the phenotypic presentation. You can find something on that is adolescents. They have a second two peak of the disease. This is a common peak, and this is in the elderly. The pathophysiology would be different. The male, we can find this disease in males much more than in female. The male osteosarcoma is when it happens, is younger than female and related to the rapid growth of the bone and the higher odd ratio in the kid that have a higher body weight. It seems to be all of this is related to the growth. This we come back to the survival rate of the osteosarcoma in Thailand. Like I said before, in international level, the survival rate is around 65%. But in Thailand, it's just only 35%. It's very lesser than the international. Even we have the standard chemotherapy, the survival is still low. When we expand deep in the data, we found that the presentations of the osteosarcoma in Thailand is more late. We have a more patient that's a presentation and the advanced state. And secondly, this is very important, is a cooperation of the treatment. We found that most of the patient is very poor because when you come to the doctor always say that, okay, we need to do amputation. The amputation is the only way for the treatment. And when you got the cancer, the treatment, it might be not success. All of this mindset is transferred to the patient and get the cooperation is quite poor. That's why this would be fixed first. Just only this thing, if we fix it, so it means that if we can detect the patient earlier, or we can make a patient get cooperation with our treatment more than before, we would be can rising up to allow 20% of the patients for the survival. This should be done first, okay? And this is also transfer this knowledge to our young medical doctor and in the orthopedic society to make this thing, at least we can help 20% more. When we do the when we get the genomic era, we try to find what's the exactly pathophysiology mechanism of this disease. The clue is we know that this disease directly related to the Rifamini syndrome and retinoblastoma syndrome, which is a cancer predisposition syndrome. It makes us curious that P53 and retinoblastoma would be the important driver. We found 90% of osteosarcoma in the referral, and we found 40% of osteo happen in the retinoblastoma syndrome. The answer is more export after we get into the genomic era. We do the exome sequencing, do the germline sequencing, and we found a little different story. It's just only 10% of the osteosarcoma that related to the cancer predisposition syndrome. However, P53 and retinoblastoma is the important driver because of more than half of the patients have this mutation, and it's become the corner driver of this. And in one piece of the tumor is very heterogeneity. They contain around 10 Khon of the sarcoma in that piece of the tumor. And the one thing, the pathophysiology, most of them, 90%, is still caused from the de novo mutations of the osteoblast. When we do when we have the GWAS study, we can confirm that all of the SNP that related to the growth is a main factor. It becomes the internal susceptibility of this sarcoma. It seems to be the genomic study can give us the more information about the pathophysiology, but the genomic study is still not directly guide the treatment nowadays. But one thing that another application that it would do is a liquid biopsy. Osteosarcoma is still one of the very difficult in terms of the monitoring the disease. If you know that when we try the new chemotherapy, we use the RECIST criteria to monitor it is respond well or not well for the new chemo drug. But the RECIST criteria is the imaging criteria. When the osteosarcoma respond to the chemo, the size is not shrinking down. It just turned to be the good bone. So the RECIST is based on the reductions of the imaging. It means that we still haven't have any good biomarker to monitoring around of the disease. Our group focusing on the cell-free DNA because we found that the cell-free DNA is one of the good footprint, and we need a very high specificity of the biomarker in terms of using for the monitoring, or if we want to use them to change the treatment. Okay, cell-free DNA, most common of the cell-free DNA that's come from the white blood cell. But when we got a cancer, we also can find a circulating tumor DNA as well in the circulation. And this group are starting to focus on this to identify the new biomarker. All right. So, but the problem is the cell-free DNA that's used in other kind of the tumor, it has to have a very signature mutation. For example, you can use cell-free DNA in lung cancer and can use the cell-free DNA to change the treatment, to prescribe the new targeted therapy, because we know that the lung cancer has the EGFR mutation. If you can find EGFR mutation in a piece of the DNA, you can use that to change the treatment, right? And the other kind that you can use is if you can see, can identify the abnormality of the piece of the DNA, for example, the gene fusions or the copy number, you can use that as a clue to make that piece of the cell-free DNA to become the biomarker. But the problem is the osteosarcoma have no any signature mutation. Every osteosarcoma, the mutation is very heterogeneity and have no pattern. The question is, how can we use the cell-free DNA to be the good biomarker for osteosarcoma? Our team tried to review more, and we know that two biological differentiation between the tumor and normal cell is the status of the chromatin and the DNA. The tumor tend to have the open chromatin, and the DNS will chop the DNA more frequency and get a smaller piece of the DNA than the normal cell. We call the fragment, the smaller fragment. And we try to analyze the fragmentomics of the DNA on this study. Okay, we try to review the smaller fragment of the cell-free DNA is have not just only found in some cancer, but it's found in a lot of types of the cancer. And we go to study use this to study in osteosarcoma. We set up the study, and this is very impressive study. When we look at the amount of the cell-free DNA, this is a healthy, just only amount. We can find that the higher level of the cell-free DNA in osteosarcoma much more than the healthy. And when we look at the size of the DNA, the normal tend to have a larger piece of the fragment, but in the stage 3 and stage 2 of the osteosarcoma is have a smaller size than the normal people. When we just use only the amounts of the DNA level to detect the diagnostic performance, we found that it's got 85% sense and 93% specificity. And when we use the fragment size, we got the higher sense and specificity in terms of diagnosis. When we combine these things together, we get 100% of sense and spec. From this result, it's very amazing me, but it's not good enough because we never require the diagnostic biomarker for the osteosarcoma. Osteosarcoma, it doesn't like liver cancer, small cancer in a big, large organ. You need something to early detection, but we never require that on osteosarcoma. That's why the biomarker should be better than that. So it should have the prognostic marker in terms of you want to use them to monitor the disease. Our group study more to expand on this more and more to try to find another option and another knowledge that used, and they found that when you look at the osteosarcoma patient itself and they map the site distributions of the fragment, and we found that if the mean fragment is larger than 150 base pair, this group of the patient have a very good prognosis. Comparing the one who have a subpeak, many subpeak, and the fragment is less than 150 base pair, they become the independent prognostic factor of the osteosarcoma, and this prognostic ability is better than the tissue necrosis from the chemotherapy. This also an interesting result, but it's still not good enough because when we have a discussion in the lab, we found out how can you prove that the small fragment just exactly come from the tumor itself. Okay, so we set another operation, try to identify that, try to prove that the small fragment does exactly come from the tumor. So we got these results. We do the copy number of the variation by doing the low pass sequencing. This is the information of the white blood cell of the patient. The copy number is 2N. That is normal copy number variation. This is the tumor. They have a gains and loss and very heterogeneity in the copy number in the tumor chromosome and the DNA. When we get the cell-free DNA non-filter to perform the same thing, it seems to be, but it's not clearly. But when we select just only the small piece of the DNA to do the copy number, and we find exactly confident of this piece to the tumor itself. So for this study, it can prove that the small fragment is very good to use to become the good biomarker to monitoring for the osteosarcoma. So the genomic study, it can make us more understanding about the pathophysiology. And the genomic also one of the good candidates to use as a biomarker, particularly in the monitoring. However, the treatment of the osteosarcoma is still based on the protein and immunology technologies. We try to review back from the study of clinical trial in the osteosarcoma this last 2 decades. Most studies focus on the cytotoxic agents, some of the targeted therapy and some of the immunotherapy. But in the last decade, it tends to be more to use the immunotherapy and targeted than the chemocytotoxic agents. And just only 2 trials that can pass to the phase 3. Both of them also in the category of the immunotherapy. And when we review the current trial that's run in the US about the osteosarcoma treatment, all this are focusing on the cell surface, signaling immunology that's based on the proteomics. That's why our team also have to do some things about this, and we expand our study in the proteomic study. We also do the proteomic as well, because we have a tissue, we have the cell. We use many scenarios of the tissue to do the proteomic. We get many candidates of the target. We do the validations, we do knockdown. They have a good performance. We do another proteomic. We got the candidate. We do the animal study. It is also the good candidate. We do a lot of proteomics from our tissue that we have. We got many candidates, but the question is how can we push this all candidate to become a novel target? Because the ecology system, we don't have the pharma company, so this is very difficult for us to introduce this thing to our friends, to a partnership. So one thing that we can do is repurposing technologies. That is another research that is make us can put this thing to the clinical application. We do all systemic review about the proteomic study, osteosarcoma that I ever had. We match with the medicines. Okay, we can from this data we can get some data that's related to the chemo drug that we can introduce another indication for it. Like for example, this is our result from that systematic review. We got one candidate that is the chemotherapy for the leukemia, and it have a capability and a chance to use in the osteosarcoma, and we got published on the modern pathologies. But the one thing that very interesting is a non-oncological drug. We get a list for the non-oncological drug that's been used in the market and is never used in to treat cancer before. The good thing is all of this drug, they have a exactly therapeutic range. That's we can use this therapeutic range to screening which one effective or not effective. We have a lot of risk of drug. Just only this one, mycophenolic acid. The functions of this drug just below the upper level of therapeutic range. The other drug, they have effects, but the effect, the level of the effective is to go beyond the therapeutic range. It means that we cannot use. This strategy is very good to screening out the drug. So interesting, we got the mycophenolic acid and we go deep to study of them. We compare them with the current chemotherapy and we get the not bad result because at the level that therapeutic use, the function of this is very comparable to all kinds of the chemotherapeutic drug. We find the molecular functions of the in vitro study. We do all assays that we can do in vitro study. And finally, we do it in the animal xenograft model. And we found that just only a few doses they can control the osteosarcoma tumor very well. And just only a small dose of the medication, they can control the metastasis in the mouse models. That of this study is make us, and when we review the mechanism of this drug, we found that the MPA is being known as an immunosuppressor drug. The doctor always use this medicine to prescribe for the organ transplant patients. And because of the mechanism function, it share the mechanism function with the metastasis. But they stay the lower stream of the mechanism. It means that it's more precise and less toxicity than the metastasis. Because of the functions, because of the mechanism that we proved in vitro and in vivo study, we pushed this mycophenolic acid to the clinical trial phase 2 at last 3 years in the collaboration with 5 universities across the country. Of this, for this year, the study is already finished. Honestly, the result is negative. The negative of this result, it might not because of the not good mechanism, but this time because of the medication that we have, they have very high toxicity by the gastrointestinal irritations. The molecular mechanism is still promising and still good. So this time we forgot to how can we modify how can we modify the releasing ability of this drug, and it might be able to use for treatment of cancer in the future. Okay, I and my group is still looking for the special approach by using the new technologies, by collaboration with the phenome in Khon University, and how can I increase the survival of the patient osteosarcoma. So we still focus in the micrometastasis, intracirculating cancer cells. We look at an organ-based strategy because the lung metastasis is we consider to become the last battlefields, because if we can control the metastasis in the lung, we can control the disease. We still interested in oncometabolics, and the immunotherapy strategy is still useful in this. So this is all. Thank you to all supporters and all collaboration of for the osteosarcoma discovery. So thank you very much.
Thank you, Associate Professor Domnang Pruksakorn, for this beautiful talk, and you show us the detailed studies on osteosarcoma using various genomics. Any questions from the audience? Professor Ellen Holmes, please.
Really interesting talk. How does the protein profile differ from primary lung cancer in the metastases? Is there a difference if you look at the proteomic profile between the metastatic lung and the, from the osteo and the primary lung cancer?
I think because of the speaker, I cannot hear questions.
Could you try the questions again, please?
Sorry. How does the proteomic profile, the proteins, differ from primary lung cancer if it's a secondary lung cancer from osteosarcoma?
Professor Mina, how the protein profile is different from the cancer itself and the metastasis, right? That's a very good question. This is very difficult for me to get the metastasis tissue. That's we never done it before, for sure. But just only a few cases per year that we can get the tissue from the lung, and most of the case is embedded in the paraffin box. So we still don't have the fresh tissue that available for us to study, compare between the original tissue and the lung tissue. We know that the new mass spectrometry is a very good to study in the paraffin box, the protein. If it's available, I think it will be get the answer because we can take the sample from the paraffin. That will be get another profile that will be very interesting.
Thank you. Thank you for the question as well. Is there any other questions from the audience? I think we have time for one more question from Jan Thidachip, please.
Thank you. Thank you so much for a very nice talk. I have a question about the CNV profile and how much does it cost per sample?
I don't know exactly the cost. Do you mean the cost, right?
Yeah. I mean, as you show that it's low pass, right? The compared to the low pass whole genome sequencing, right? But you show if you can get the small size and then perform the sequencing, and then you can get profile. But I'm not sure how much does it cost for
I'm sorry, I don't know the exactly cost as well. But from this publication, we also got a very little budget. We just do only 3 cases of the study to do the whole genome sequencing of the tumor and then do the sequencing of the cell-free DNA. When we submit the paper, the reviewer also want us to do more, and it may cost more, and we don't have many left. And we just tell that, okay, this 3 case, it would be enough to prove that is concordance of this. But it mean in the future, it means that after we prove of this, for sure, we're going to set another work to prove more. That's to prove that the concordance between the tumor tissue and the cell-free DNA. After that, in the practical use, we will never use this. We will no need to do the sequence anymore. We will just only detect the small piece of the DNA. That's it. When you have the small piece of DNA, that's it. You have the cancer. The cancer is come back. Something like this.
Thank you.
That will be cost you just a few thousand.
Yeah.
But in terms of the research and going to more details of this data, I was just curious, would you be looking into other technologies, for example, the long read sequencing to characterize those fragments as well? Would that be part of the plan to use like long read technologies, long read sequencing technologies to characterize those fragments?
That's a very difficult question.
Because we have experts
because osteosarcoma is very complexity of the mutations. We still keep about that because we contact doctor for a long time and how to use the long read in the application of this soon.
Thank you so much. I'm really looking forward for the future collaborations and more talks coming up this afternoon. So please give us a big round of applause to Associate Professor Damdan Pruksakorn. And